Reason why we start chapter 6 with inverse is because exponential and logarithmic functions, when they have the same base, are the inverse of one another. But I will get to that possibly in a minute. Right now I'm just going to say, talk about very quickly about some properties of exponential functions. When the base of an exponential function is greater than 1, we'll have an increasing function, and we can see that with 9, 8, 5 fourths, 3 halves, 5 halves, and 4, the bigger the base, the faster the increase. Similarly, when the base is between 0 and 1, not equal to 1, not equal to 0, but between those two, then we will have a decreasing function. And we can see that 8 ninths, 4 fifths, 2 thirds, 2 fifths, and 1 fourth are all between, those are values between 0 and 1. And the smaller the value, the steeper the decrease, the faster the decrease. Also, e to the x is our best way of, or rather e to the kx is our best way of modeling exponential growth and decay. And we will vary the decay factor k to make our most accurate models. When this value is positive, we have increasing functions. When the value is negative, when the value of k is negative, we have decreasing functions. And for any function that has a base, well, for any exponential function, we could model it with a particular base, or we could model it with e raised to a particular growth or decay factor as well. And that's what's shown here. The first function I've shown, 1.3 raised to the t, or e to the 0.262t. And there's our inverse functions again. Now, the next thing that I want to look at is the translation, how to analyze graphs to determine the translation, how they were translated, in other words, how they were shifted. We looked at these two functions in class. These are exponential functions. I've got better graphics and a little more explicit demonstration that shows that translation. The dashed line here, that is 2 to the x. Now, any exponential function that has not been shifted yet is going to be asymptotic with respect to the x-axis. In other words, it is a horizontal asymptote, and the graph of the function will never fall below it. So we will use that asymptote as a reference to figure out where the function we're going to see in a moment has been translated to. We can already see the answer down here, but here's how we do. Here's how we do that. Here's how we determine what the shift has been. Above the horizontal asymptote, we draw a line 1 unit above it. So parallel to the asymptote and 1 unit above that asymptote. And where that, where the function crosses the y-axis is also going to be where that asymptote intersects the y-axis. So that's our starting point. That is our y-intercept. We're going to examine that and see where it moved to. So now here we have a translated function. It's been shifted. How has it been shifted? Well, to determine that, we see that this, coincidentally, is the horizontal asymptote of the shifted function. And then we draw a horizontal line 1 unit above that. Draw a horizontal line 1 unit above that, and wherever that line intersects the translated function graph, that is where this point, the y-intercept, has been translated to. And we can see that as 2 units to the right and 1 unit up. 2 units to the right means that we subtract 2 from x inside the function, so that's what this is, 2 to the x minus 2. And 1 unit up means that outside the function we add 1. So that's why this translated function, this function graph right here, is 2 to the x minus 2 plus 1. Now this is the logarithm base 2 that we saw in class, and I've got a better graphic for it as well. We do the same thing, except instead of using the y-intercept, we will use the x-intercept. And so a logarithmic function, and this is log base 2 right here. You can see that for x is 2, y is 1. A logarithmic function will never have a negative value in its domain, at least an unshifted, untranslated logarithmic function. And so we have a vertical asymptote that in this case is the y-axis. And if we draw a vertical line 1 unit to the right of it, then the place where the function intersects the x-axis and that vertical asymptote will be the same, and so that is our that's our point that we're going to reference. It's the x-intercept of the function. Then we can see here our translated function has a vertical asymptote at 2. And if we draw a vertical line 1 unit to the right of it, then that that line intersects the translated function at the at this point, which was the x-intercept, but it got shifted. How did it get shifted? Well, once again, this got shifted 2 units right and 1 unit up. Now, I want to caution you that these are not always so tidy and convenient. This, for instance, this vertical asymptote of the shifted function here, it could have been all the way over here because the function could have been shifted all the way over here, or the function could have been shifted this direction. But in any case, wherever the new asymptote is, you want to draw a vertical line 1 unit to the right of it in the case of the logarithmic function, and in case of the exponential function you want to draw a horizontal line 1 unit above the shifted function's asymptote, in this case horizontal asymptote.